Okay, so welcome back, everybody. In the last two lectures, we learned a little bit about digital and analog circuits and what was important for the operation of those circuits. In this lecture, I'll summarize the key device metrics that we use to assess the potential performance of a transistor in a digital or analog circuit. We will review some of the concepts we discussed in the previous two lectures and add one or two metrics that are also important. So before I get started, just let me remind you that the current in a MOSFET scales with the width of a MOSFET. If I double the width of the MOSFET here, I'll double the current. So it's common to quote the currents when we're measuring them and plotting them in units of perhaps milliamps per micrometer of width or microamps per micrometer of width. So we'll follow that convention and do it that way because designers use transistors of different widths, so we really want to do our analysis in a way that's independent of any specific width of the MOSFET. All right, our first important metric for digital circuits is on current. And to measure the on current, we put the largest voltage available in the circuit, the power supply voltage on the gate. We put the largest voltage available on the drain, the power supply voltage. We measure the current. That current we call the on current. It's the maximum current that the transistor can deliver for this power supply. So the on current we've seen is an important metric for digital circuits because it determines the speed of the circuit. The switching time is the switching capacitance times the power supply voltage divided by this on current. The higher the on current, the faster the transistor and the circuit will switch. Our second metric is the off current. So to measure the off current, we put 0 volts on the gate and we put the largest voltage possible on the drain. The transistor should be off, so no current should be flowing. If we plot the transistor characteristic here, we'll see a sub-threshold regime when the gate voltage is below threshold. We'll see an above threshold regime when the gate voltage is greater than the threshold voltage VT. And our off current is this small current that's too small to read on this linear plot. So if we really want to read the off current, we should plot the current on a log scale. So that's what's typically done. This is the same characteristic, but now plotted on the vertical axis is a logarithmic axis. We're plotting the log of the drain current versus the gate voltage with the drain voltage applied to the power supply voltage applied to the drain. And at 0 gate voltage, that's our off current. So our off current is typically then measured in amps per micrometer of width. Now, we've seen that the off current is an important device metric because the off current determines the static standby power when the transistors are not switching. And since we have lots of transistors on chips these days, this can add up to be a significant power. Now, there's another important device metric that we haven't yet talked about, and I want to introduce here. This is called the sub-threshold swing. It's important that a transistor switch from off to on as quickly as possible and over as small a voltage range as possible. That's what would be desirable. The way that we measure that is with a parameter called subthreshold swing. So if we look here in the subthreshold regime, and if we ask ourselves, how much do we have to increase the gate voltage, delta VG, in order to increase the current in the subthreshold regime by a factor of 10? That's the subthreshold swing. So we define the subthreshold swing as being the number of millivolts we need to increase the gate voltage by in order to increase the drain current a factor of 10, an order of magnitude. We typically quote it in millivolts of gate voltage increase per decade of drain current increase. Okay. Now, subthreshold swing is an important characteristic. You'll notice if I had a transistor with a certain subthreshold swing, SS sub 1 here, and if I had a second transistor that had precisely the same on current, but that had a larger subthreshold swing, a larger subthreshold swing would mean that it would take more gate voltage to increase the drain current by a factor of 10. What I would find is that the off current has increased. In fact, it's increased exponentially, which is very bad. So it's very important to have a very small subthreshold swing in a transistor. So subthreshold swing and power supply voltage all play into power. So the static power dissipation, it depends on the off current. So it's important to have a small subthreshold swing for that. The subthreshold swing determines the off current. Now the dynamic power depends strongly on the power supply voltage squared and on the frequency. So we would like to use as small a power supply voltage as possible. And the subthreshold swing is a major factor in determining how small we can make the power supply voltage. So what we would like to do is we would like to use as small a power supply voltage as possible so that when we swing the gate voltage from 0 to the power supply, we turn the device on and we get a lot of current. We get the on current. Now, we might think that, well, one way to do that is simply to lower the threshold voltage. If I lower the threshold voltage such that VDD minus threshold voltage doesn't change, then I could lower the power supply voltage and have the same on current. The difficulty is all that is going to do is to translate this transistor characteristic over to the left. Okay, I'll have precisely the same on current at a lower power supply voltage, and dynamic power goes as voltage squared, so that's good. But look what's happened to the off current. The off current has increased exponentially. So this is a major factor that transistor designers have to worry about. We want the subthreshold swing to be as small as possible so we can use a power supply voltage that's as small as possible, but we have to be very careful about doing this that we don't increase the off current. So the subthreshold swing can be determined simply by taking 1 over the slope of this log drain current versus gate voltage characteristic. We need to minimize it to minimize the off current. We need to minimize it to minimize the power supply voltage that we need to use in order to get the on current that we need at maximum gate voltage. And one very important point is that the physics of the MOSFET dictates that the subthreshold swing can never be less than 60 millivolts per decade. And that's just comes out of the physics of the device. We will talk about that in detail later and explain where all of that comes from. But this is a major limiting factor in a MOSFET. We would like to beat this 60 millivolt per decade limit, but at room temperature, that's just not possible unless we go to some very novel types of transistors that people are still exploring with the hopes of beating this 60 millivolt per decade fundamental limit. Okay, now I want to turn for a minute to the effect of drain voltage on a transistor. How does the drain voltage affect the performance of the transistor? Well, there are several different but mostly related ways. So one way, we know that if we look at the transistor in the linear regime, the drain current is linearly proportional to the drain voltage because the device is operating as a resistor. Okay, but that's sort of the inherent property of the MOSFET. It's not a non-ideal effect of the drain voltage. Sometimes we define a metric, which is the on resistance. It's useful to know what that minimum channel resistance is. But there are other effects that the drain voltage has, which are really detrimental to the operation of the transistor as it should operate. So one of those ways is if we look at an ideal MOSFET would behave as a gate voltage dependent current source in the saturation region. The current in the saturation region would be independent of the drain voltage. Well, that's just not true in any real MOSFET. There is always some slope there, and that slope means that if I increase the drain voltage a little bit, I'll increase the current a little bit. We measure that through the output resistance, 1 over the slope of the current in the saturation regime. Okay, now there are other effects. Turns out they're all related. But if I plot the transfer characteristic of a MOSFET, say at low drain to source voltage, so I'm in the linear regime, and I plot output current versus input voltage, VGS, I'll see that the current will begin to increase at the threshold voltage. I'll label this VT lin for linear region because we're doing this in the linear region of operation. Now, I could also apply a large drain voltage to the transistor. I would be operating in the saturation regime. I could plot my transfer characteristic again, but this time in the saturation regime. And again, the current would begin to flow when the threshold voltage is exceeded. If I were to extrapolate this straight line to the origin and determine the threshold voltage, I would find that the threshold voltage is different. This difference is not a desirable effect. We generally find that the threshold voltage in the saturation region is smaller than the threshold voltage in the linear regime. We'd prefer to have a transistor whose threshold voltage doesn't change when we change the voltage on the drain of the transistor. So that's not a desirable effect. Now, another way to see this is if we plot the transfer characteristic on a logarithmic scale. We've done this to look at the off current earlier. So here's the subthreshold regime. Here's the above threshold regime. There's our on current. If we reduce the voltage on the drain to a small value and plot the transfer characteristic, we'll see that it's shifted. And if I pick a small current, maybe 10 to the minus 7th amps per micrometer of width, and I'll say that that's my threshold. If I have a current above that, I'll consider the MOSFET to be on. If I have a current below that, I'll consider it to be off. If I pick that particular current, you can see that there's a shift in the gate voltage at which that current occurs. There's a parallel shift. That parallel shift, that shift of that point with the drain voltage, is called drain-induced barrier lowering, or DIBBLE. It's the change in VG divided by the change in VD at the same drain current. Usually we express this metric in terms of millivolts per volt. The number of millivolts change in the gate voltage when we're changing the drain voltage by a certain number of volts at a constant current, this dashed line here. Okay. Now, I could also note that this is very closely related to threshold voltage. The threshold voltage in the linear regime is the gate voltage it takes to reach this critical current that we consider the device to be on at. The threshold voltage in the saturation regime is the voltage it takes to reach that critical current when we have a large voltage on the drain. So the difference in threshold voltages that we saw on the previous slide and this parallel translation of the subthreshold characteristic are really the same effects looked at in two different ways. Both occur because of this effect called DIBBLE. So all of these non-ideal effects, the threshold voltage dependence, the non-infinite output resistance, the DIBBLE that we read from the subthreshold characteristic, they're all due to the same physics. A single metric can be used to assess them all for digital circuits, and we will discuss the physics of what's causing these effects later on in the course. But for now, we simply want to remember this term DIBBLE. Drain-induced barrier lowering is the way we quantify this undesirable effect of the drain voltage on the transistor characteristic. So once again, we have a mathematical definition. It's easier to understand what it is by looking at one of the transfer characteristic plots and seeing this parallel translation. We measure it in millivolts per volt. Typically, it's the millivolt change in the gate voltage per voltage change in the drain voltage at a fixed current in the subthreshold regime. The higher the DIBBLE, the more sensitive the threshold voltage is to the drain voltage, and that's not a desirable characteristic for a transistor. Also, the lower the output resistance would be if we look at the output characteristics of the transistor. So we have these four key important metrics for digital circuits: on current, off current, subthreshold swing, and DIBBLE. And you should spend a little bit of time and familiarize yourself with these definitions, because we will be referring to them many times as we explain the physics underneath each of these parameters. You might practice a little bit. Here's some measured data from 32 nanometer N-channel MOS technology. And if you eyeball some numbers off of this curve, you should be able to get numbers for these four device metrics that are close to the ones that I got. Now, as we've mentioned, there are complementary devices. There's an N-channel device, which is what I've been talking about. There's also a P-channel device where we apply negative voltages to the terminals. The current flows out of the drain instead of into the drain. These are IV characteristics for the P-channel device in the same technology, and you might practice by extracting the four key digital device metrics for this P-channel device as well, and compare them to the values that you saw in the N-channel device. Okay, so those are digital device metrics. There are only a couple of analog device metrics that are easy and quick to pull out of measured characteristics. So we'll talk about a couple of those now. So remember, in analog characteristics, the maximum gain that we can get out of a transistor is minus G sub m R out. That is, G sub m is the transconductance, the small signal transconductance of the transistor. R out is the output resistance of the MOSFET. So both of those are important device metrics for analog applications. There are others, FT, Fmax, noise, mismatch, etc., that we would also be looking at, but these are the first two that we would look at to see if we have a device that it's worth looking deeper at. So just to refresh your memory, what is transconductance? Transconductance will have an IV characteristic at a certain gate voltage. If we have an IV characteristic at a little bit smaller gate voltage, we'll get less current. The change in drain current divided by the change in gate voltage, if the gate voltage is a small change, is the small signal transconductance. Generally, we'll quote it in units of millisiemens per micrometer of width of the MOSFET. We can also take the slope of the output characteristic. 1 over that slope gives us the output resistance. We generally do that at the highest drain voltage that's applied to the transistor. So we can extract those two critical parameters to see how it works. Here is some 65 nanometer technology. That means the gate length is about 65 nanometers long. And we can just read off of this curve and do some quick estimates of what these parameters are. The transconductance, we've seen these before, so I'll just remind you, we did the transconductance, it was about 1 millisiemen per micrometer. We did the output resistance, it was about 7 kilo ohm micrometers. And we did the self-gain. It wasn't big, but it was big enough to do some analog circuits with about 7, on the order of 10. Now, these are the characteristics. This is the 32 nanometer technology that I showed earlier, where we extracted the digital metrics. You could go ahead and extract the analog metrics. What we would find is that this is a shorter transistor. It's got significantly higher transconductance. That's good. It's a better amplifier. In this case, it's 2.5 times larger than the 65 nanometer technology. But note also that the output resistance is more than 2.5 times smaller than that of the longer channel device. So when I put the two together and compute the self-gain, this device actually has a smaller self-gain than the older and longer channel technology. So this is the reason that device designers often, analog designers often prefer to work with longer channel length transistors to get higher gains. So just to summarize quickly, we have 4 key digital device metrics. You should be sure that you're familiar with how those are defined and how to extract them from an IV characteristic. We have 2 key analog device metrics that we begin with before we would look deeper in FT, Fmax, noise, and things that are more complicated to measure. You should be familiar with those as well. And then we've referred to a couple of other parameters that will come up in our discussions later. VT-lin, VT-sat, the drain saturation voltage, threshold voltage is another one. So you should be familiar with the definitions of these parameters and how to pull them off of a measured IV characteristic. So let's summarize device metrics. We've talked about some key metrics for digital applications. There are really 4 of them: on current, off current, subthreshold swing, and dibble. We've talked about some key device metrics for analog. The 2 most important are transconductance and output resistance, and you put the 2 together and you get self-gain. Given a set of IV characteristics, be sure that you can extract these parameters. Now, our focus for the remainder of the course is going to be to explain, in terms of the underlying physics of the transistor, what controls the performance of these device metrics, what controls the magnitude of the on current, the subthreshold swing, etc. All right, so that does it for device metrics. Now, what's next? So device metrics are a way that device engineers take a quick look at a device and are able to ascertain that this device looks like it would be promising in digital or analog applications. Now, for circuit designers to actually design circuits, they need much more than a few simple metrics. They need a complete circuit model that allows them to do a detailed analysis. The topic of the next lecture will be just a brief introduction to what's known as compact circuit models that allow designers to design complex circuits with transistors.